Welcome! So today we're going to pick up here at example 8.4, and we're also going to look at the definition of a vector space over a field, and hence the definition of a field also. And we will have a little look at the concept of an inner product and some examples on that. Okay, 8.4. Let U and V be three-dimensional vectors over the field of real numbers. Suppose these two are parallel, U and V, and that they're the sides, parallel to the sides of a parallelogram. So let's draw a picture, and that's much like what I have here on the left. So drawing a picture of this. Okay, so here I've got a parallelogram. So suppose that we have a vector u parallel to that side, and likewise over here, and v parallel to this side and to this side. And we want to calculate the area of this. So let's let theta be the angle between u and v. And so our area, we can think of this as the area of a rectangle, but what we need to do is construct an additional vector across here with right angles to V, and let's call this Q. So that if I chop this off, say with scissors, and put it over here, let's draw a dotted line where we would place this rectangle here, all of this, has the same area as the parallelogram. Okay, so we have that the area of the parallelogram is equal to the norm of the vector Q multiplied by the norm of the vector V. So this segment times this segment gives us the area of this rectangle, which is the same as the area of this parallelogram here, because we can cut this end off, this little triangular piece, and place it over here. Okay, and so let's simplify this. Now we have a relationship between the norm of Q and the angle theta and U, because remember that sine is opposite over hypotenuse, so sine of theta is the norm of Q over the norm of U. And so we can rearrange this equation solving for the norm of Q. So the norm of Q is equal to the norm of U times sine of theta. And incidentally, this must be positive because the norm of Q is positive. All right, so let's sub this in. So we have the norm of U sine theta times the norm of V. And let's now rearrange this, moving the norm of V over left. So expressing this as the norm of U times the norm of V sine theta, where theta is the angle between U and V. Okay, there's a formula for this. This is the norm of the cross product of U and V. So what we've done then is shown that the area of the parallelogram is the norm of U cross V. All right, let's move on to the next page. Where we have the definition of a vector space. A vector space V is a non-empty set of vectors over a field K. Now that is double struck to suggest that I'm talking about a field. It's usually the set of real numbers when we're talking about relatively elementary vector spaces. Now that field of scalars needs to have the numbers 0 and 1 in that field. Okay, so this vector space is a set of vectors that satisfies the following axioms. So we have 8 axioms of a vector space, but we can think of the first 4 as being axioms for what we call an abelian group. And the first 3 are axioms for a group. So the first one, addition is associative. So we can move the brackets around when we're adding vectors. All right, so this needs to be satisfied, that we can move the brackets from around the u and v to be around the v and the w. So 0 is neutral. Now what this means is that 0, the 0 vector plus any vector, say u in v, is equal to u, and it's the same as u plus the 0 vector. All right, so this happens for all vectors u in the vector space uppercase V. So the 0 vector is special in that way. For all u in V, there is an element minus u also in V, such that u plus minus u is the 0 vector. So this one is a little bit perhaps too brief the way it's written. So let's rewrite this. For all u in the vector space V, we can always find another vector v in the vector space V such that u plus v is 0, the 0 vector, which is the same as v plus u. All right, and we just name that minus u. So name this v equal to minus u. All right, so the 3 of these axioms, if they hold for v with addition, then we call that structure v together with addition, we call it a group. If the 3 of these axioms hold for that set together with addition. Now, if u plus v is always equal to v plus u, in other words, we have commutativity, then the 4 of these axioms make this structure an abelian group. The 4th one is commutativity of addition. Okay, and if we have all 4 of those, we can call this additive structure an abelian group. Abelian is named after a person, Niels Henrik Abel, but it refers to commutativity. Okay, the 5th axiom. So these are about scalar multiplication. For all scalars k in the field uppercase K, and vectors u and v in the vector space V, k times u plus v is ku plus kv. For all scalars a and b in the field K, and vector u in the vector space V, a plus b in brackets times u is a times u plus b times u. Axiom 7, for all scalars a and b in the field of scalars k and vector u in the vector space V, a b u is a times b u. And finally, the number 1 in the scalars is neutral in the sense that 1 times u is just u. So if all 8 of these axioms hold, then V together with scalar multiplication and addition is a vector space. Okay, we've got a theorem. Theorem 19, let V be a vector space over the field K. For any scalar k in the field K and 0 vector in V, then k times the 0 vector is 0. So this theorem is a consequence of these axioms. Right? Under the assumption that we have a vector space, then these axioms hold, and so we can show that these properties hold following from the axioms. All right, so for example, this one is a consequence of 3 and 5 together. All right, so you can go ahead and use axioms 3 and 5 of a vector space to show that property 1 of theorem 19 holds. And then for another example, this one is a consequence of number 7. Okay, next. For 0, the 0 number or 0 scalar in the field of scalars, and the vector u, 0 times u is the 0 vector. Notice there's a difference here. This is not bold, this is bold. So this is the 0 vector, this is the 0 scalar. Different concepts. Okay, so in other words, 0 times u is the 0 vector. Number 3, if for some scalar in the field of scalars, some scalar k times the vector u is the 0 vector, then either or both k is 0 or u is the 0 vector. For any scalar k and vector u, minus k times u is k times minus u. Again, that's from 7. Okay, so this is our definition of a vector space, and this theorem 19 is a consequence of the definition. So let's have a look at a few examples of vector spaces. So Kn over the field K. And so this would be an n-tuple where the components of your vector are elements of the field K. Okay, some examples. The set of real numbers are 2, are 3, are n. Let's talk about these one by one. So the field of real numbers, you can think of this as the number line if you like. Let's find 0, there's 0. And so suppose we have a number, let's just call it p. Now it could be something like 4. Okay, so how do we think of vectors in this concept? Well, we have a vector from O to P. Let's call this R. And remember, in terms of position vectors, this is P minus O. But O here is just the origin, 0, the number 0, and P is a number. So this would be the number P. And so the direction is according to whether that number P is positive or negative. Right? What's the magnitude of R in this case? Well, it's just the absolute value of the number P. Okay, now what about R2? So in R2, we can think of vectors in this as arrows in a two-dimensional space. So for example, the vector from O to the point P, again we can call this R, so R equals OP, and taking points P minus O. And so R2 is the set of all such vectors that would correspond to two-dimensional arrows. And so on and so on. All right, another example. The set of all univariate polynomials P of t, where the A0, A1, A2, and so on up to AN are elements of the field K. So this has width, all of the A subscript j belonging to the field K, the field of scalars. Now, for these to be vectors, we need the n to have finite degree. So all of the highest degree, lowercase n, have to be less than or equal to some particular fixed uppercase n for this to be a vector space. Okay, the space of all m by n matrices with entries in the field K. Let's look at an example. So if we just take A equal to A11, A12, A13, A21, A22, and A23. So this is in a space of all 2 by 3 matrices with entries in, say, the set of real numbers. Right, so you can flatten this out and call this a 6-tuple. So A corresponds to the 6-dimensional vector A11, A12, A13, A21, A22, and A23 in a 1-to-1 correspondence. So you can take these and think of these as row vectors or column vectors if you like. Okay, let uppercase f of x be the set of all functions sending the set x to the field K. Okay, so this forms a vector space also. For example, scalar addition, or sorry, scalar multiplication. How does this look? Kf is applied to x is k times f of x, and addition of vectors, the functions being considered as vectors, so f plus g acting on f is the same as f of x plus g of x. Okay, so these form a vector space also. Let's talk about subspaces of a vector space. Let V be a vector space over a field K, and let W be a subset of V, so that every element of the set W is an element of the set V. W is a subspace of V if W is a vector space over the field K. So W itself needs to be a vector space over the field K also, together with being a subset. So if we have a subset of a vector space and that subset is also a vector space, then it's a subspace. Theorem 20, let W be a subset of V, where V is a vector space. So let's add that in. Then W is a subspace of V if the following conditions hold. The zero vector is in W. W is closed under addition and scalar multiplication. So if you have a subset of a vector space where these two things hold, then it's actually a subspace. So it will be a vector space in its own right. Every vector space contains at least two subspaces. The subspace containing the zero vector and the subspace V itself. So note, these are subsets. And so I can use the subset or equal to symbol, and V is a subset or equal to V. All right? So these are subsets, but they're also vector spaces, and so they are subspaces. These two are subspaces of V. Example 8.5. let V be the vector space R3. Let U be equal to the set of all vectors A, B, C, where A, B, and C are equal. Show that U is a subspace of V, and we're going to use theorem 20 to do that. So let's take an arbitrary element of the set U. So we'll say for all vectors U belonging to the set U, meaning this, there exists a scalar K. Now the field of scalars here is the set of real numbers, such that the vector U is K times the vector 1, 1, 1. Okay, because if A, B, and C are equal to each other, then you can call them all A, for example, factor that A out, and you have A times 1, 1, 1, right? And so we can always express our vector U in this set in this form. All right, so let's just check now that these two conditions of the theorem hold. So is 0 an element of U? Yes, it is. So the 0 vector, which is 0, 0, 0, is an element of this set U, since 0, 0, 0 is equal to 0 times 1, 1, 1. And 0 is a real number. So number 1 holds. Okay, let's check that W is closed under addition and scalar multiplication. Now what does this mean, incidentally? It means that if W1 and W2 are elements of the set W, then W1 plus W2 is also in the set W. So that's closed under addition. Now closed under scalar multiplication is if K is a scalar, so in the field of scalars, then K times W1 is also in uppercase W, the set W. Okay, so this is closed under scalar multiplication. All right, so let's check that here. So let U1 be equal to K1, 1, 1, 1, and let U2 be equal to the vector K2 times 1, 1, 1. So we're sure then that they're in this set because they're of this special form. So, and they are arbitrary, right? They are arbitrary elements of this. We haven't chosen any specific ones. They are arbitrary elements of the set U. So then adding, so U1 plus U2 is K1, 1, 1, 1, plus K2 times 1, 1, 1. And then so by which axiom here? By number 6, going this way, we can express this as K1 plus K2 times the vector 1, 1, 1. And so since K1 plus K2 is a real number, this vector is in the set U because it's of this special form. So it's in the set U since the set of real numbers is closed under addition. Okay, let's check closure under scalar multiplication. So let k be an element of this field of scalars, so the real numbers, and u be equal to k, k1, 1, 1, 1, where k1 is also in the field of scalars. Okay, so what we need to check then is that k times u is also in uppercase U. So that's k times k1 times 1, 1, 1. And then according to one of the axioms, and it looks like the seventh one, this is k times k1 in brackets and then times the vector 1, 1, 1. And so because multiplication of scalars is closed, I mean the set is closed under multiplication of scalars, so this is in the field of scalars, so this must belong to the set U. All right, and so by theorem 20, U is a subspace. Right, the result follows. I don't have space here to write that, but the result follows by theorem 20. So just put dot, dot, dot. Okay, example 8.6. Let V be the vector space consisting of all 2 by 2 matrices with entries in the set of real numbers. And let uppercase U be the set of all such matrices where the bottom left entry is 0 and the top and the other entries are real numbers. Show that U is a subspace of V. So we need to check this according to theorem 20. So first we'll note, since 0 is a real number, the matrix 0, 0, 0, 0 is an element of the set U. All right, so this is the first one checked. Now let's move on to the second condition of theorem 20. So what we need to do now is take two arbitrary elements of this set U and show that their sum is an element of the set U also. So we'll say let U1 be equal to A1, B1, 0, C1, and U2 be equal to A2, B2, 0, C2. Let both of these be elements of the set U. Now let's add them up and have a look at it. So U1 plus U2 is equal to A1, B1, 0, C1 plus A2, B2, 0, C2. Now, matrix addition says that we add the entries in the same position. So in other words, A1 plus A2, B1 plus B2, 0 plus 0, C1 plus C2. Now 0 plus 0 is 0, so this is of that form because the real numbers are closed under addition. So this is an element of U since R is closed under addition. Okay, so finally let's take, so now let K be an element of our field of scalars, a set of real numbers. And let U be equal to A, B, 0, C belong to the set U. So then Ku is K times A, B, 0, C. Multiplication here gives us K times A, K times B, K times 0, which is 0, and K times C. Now, since the set of real numbers is closed under multiplication, this is also an element of U. So it's closed under multiplication. Okay, so by theorem 20, U is a subspace of V, the set of all 2x2 matrices with real entries. Okay, next page. So now let's talk about inner product spaces. So this is somewhat abstract, this section. An example of an inner product is the dot product. Gives us a very elementary example of an inner product. But not all inner products are the dot product. An inner product on a vector space V over a field K is a binary operation on V such that for each vector, lowercase u and lowercase v in the vector space V, the inner product, denoted like this with a pointy bracket. Now this is not talking about a vector, this is the inner product. This is a scalar in the field of scalars satisfying these three conditions. The inner product of V with V is greater or equal to 0, and equal to 0 if and only if the vector V is 0. The inner product of U with V is equal to the inner product of V with U for all vectors U and V in the vector space V. And for all U, V, and W that are vectors in the set of the vector space V, and all scalars K1 and K2 in the field of scalars K, the inner product of K1U plus K2V with W is equal to K1 times the inner product of U with W plus K2 times the inner product of V with W. If V, the vector space, has an inner product, then it's an inner product space. Okay, so R3 is an inner product space because it has an inner product, the dot product. Example 8.7, let V be Rn, so n-dimensional space over the field of real numbers. Show that U dot UV, being U dot V in this case, is an inner product on V. All right, so what we need to do is check these three axioms hold for the dot product. So the first one. So let's take a vector V in the vector space V, here being Rn. So it's n-dimensional, so we can express it in terms of n components. So then V equals V1, V2, etc. up to Vn. And so the inner product of V with itself, in this case, since it's the dot product, so that's V dot V, which is V1 times V1, so V1 squared plus V2 squared, and so on, plus Vn squared. Now this is always greater or equal to 0. Can this ever be negative? No, because these are all squares. It's a sum of squares, so it must be greater or equal to 0. Okay, now V, inner product V is 0 if and only if the vector V is 0. So first, suppose, or first take inner product of 0 with itself. What is this? 0 vector dot 0 vector, which is the sum of a bunch of zeros. So 0 times 0, etc. n squares of 0, which is equal to 0. Okay, conversely, suppose inner product of v with itself is 0. Well, since we're talking about the dot product in this case, then v dot v is 0. What is this? It's v1 squared plus v2 squared, and so on, up to vn squared is equal to 0. Now this can only be 0 if each of these are 0. So we must have v1 equal to 0, v2 equal to 0, and so on. All of the entries or components of that vector v must be 0. Okay, so we're done checking number 1. Let's move on to number 2. Inner product of u with v is u dot v in this example, and we know u dot v is equal to v dot u, so that's the inner product of v with u. Okay, that was easy to check. Let's move on to number 3. So we've got, suppose k, okay, so I should say let k1 and k2 be elements of the set of real numbers, and let u, v, and w be vectors. So then what we have is k1u plus k2v inner product with w is the dot product of k1u plus k2v with w. And we can expand this dot product in the following way. This is k1u dot w plus k2, that's a single v, not a v1, k2v dot w. Okay, and so this is k1 u inner product w plus k2 v inner product w. Okay, so we have checked that all 3 of these hold, and so we deduce then that the dot product is an inner product. So hence the dot product or scalar product is an inner product on R3. Okay, now let's move to an example on the next page. Where the inner product is not the dot product, it's actually an integral. All right, so let uppercase F, where this AB is an interval, let this be the set of all functions sending the domain being the interval from A to B. In other words, this is the set of all real numbers between A and B. Mapping that to the set of real numbers. Show that inner product fg being the integral, or the definite integral of the product of f and g from a to b, show that that is an inner product on the space uppercase F. Okay, so we need to check those three conditions of the inner product. So the first one would be F inner product F. This is defined here as the integral from a to b of f of x times f of x with respect to x. So that's the integral of f of x all squared with respect to x between a and b. And remember what this represents. This represents an area under a curve. So this is an area put a there and b there in our diagram. And so we have some function, might look like this. So this represents the following area. Now, since we have a square that we're integrating, this is above the x-axis or on the x-axis, so that area must be greater or equal to 0. Okay, now can it be equal to 0? Yes, it can. It can be equal to 0 if we have our function being just the 0 function. So if f of x is equal to the 0 function, then clearly the inner product of f with itself is just the integral from a to b of 0, which is, so the integral of 0 is 0, but then we sub in a and b, we still get 0. Okay, so if f of x is 0, then our inner product gives 0. Now conversely, if the area is 0, then we must have f being 0. Okay, so we have now checked the first condition of calling this an inner product right here. Okay, so let's move on to the second one. Inner product of f with g is defined here as the integral from a to b of f of x times g of x dx, but multiplication is commutative because this is just ordinary multiplication. So this is the same as g of x times f of x integrated with respect to x between a and b. And that is g inner product f. Okay, so we've checked the second condition for an inner product. Now let's check the third condition. So for all f, g, and h belonging to f, a, b, so in other words, f, g, and h are functions from the interval a, b to the set of real numbers, like what we have there. And let's choose some scalars, or a scalar k in the field of scalars. In this case, it's the real numbers. We need to check that kf plus we need two scalars, right? So k1 and k2. So k1f plus k2 G inner product with H equals the integral from A to B K1F plus K2G applied to X multiplied by H of X with respect to X is equal to, well, we just multiply this out and we've got K1 F of X times H of X plus K2 G of X times H of X, and then integrate. Okay, now we can break this up as a sum of two integrals. Oops, that's H of X okay, and this is the sum of two inner products, K1F inner product H plus K2 G inner product H. Okay, so we have checked the three conditions to call this an inner product, and so this inner product is an inner product. So we've been talking a lot, just mentioning the word field, and so now let's talk about what a field is. Let F be a set and let plus and times be binary operations on F, so just like what you know of addition and multiplication. F with plus and times is a field if it satisfies the following conditions. So we have 8 axioms of a field here. Addition is associative for all scalars A, B, and C. A plus B added up first, and then plus C is the same as A plus B plus C. Addition is associative. Okay, if you can move the brackets around. 0 is neutral in the sense that 0 plus A is A, which is A plus 0 for all elements A of the proposed field F. Okay, for all A in F, we can always find another element B, which we call minus A, such that A plus B equals 0, which is B plus A. Right, so inverses exist. Let's rewrite this. For all A in F, we can always find B in F such that A plus B is our neutral element. In this case, it's called 0, which is B plus A, and name or call B equal to minus A. Okay, if we can always find such an additive inverse for every element A. Okay, so for all A and B, now this time B is not the additive inverse of A, so for all A and B in F, A plus B is B plus A. So addition is commutative. All right, so the first three of these make F together with addition a group. And this property here is commutativity of addition. If you have all four, then you have an abelian group F together with addition. All right, now multiplication. Multiplication is associative. You can move the brackets around when you're just multiplying, or you can leave them off entirely, right? Because multiplication is associative. All right, so this being a condition here of a field. 1 is neutral in the sense that 1 times A is A, which is A times 1 for all elements A of F star. F star is the set of all non-zero elements of the field. So we throw out the zero element when we're talking about this. And here we have a set difference. So the set of all elements of F without zero, set difference. We're throwing out that neutral element 0. For all A non-zero elements of the field, we can always find an element B called B inverse that is in F such that A times B is equal to the neutral element 1, which is B times A. Okay, so let's write more details on this. So for all A in F without 0, so F star, we can always find B in F star such that A times B is equal to 1, which is B times A, and we call this B A to the power of minus 1, or 1 over A. If you're talking about something like the field of rational numbers or the field of real numbers. For all A and B in F, A times B is B times A, so commutativity of multiplication. Okay, last one, multiplication distributes over addition. So for all A, B, and C in F, A times B plus C is A times B plus A times C. So if all 9 of these axioms of a field hold, then that set together with addition and multiplication, this structure, algebraic structure, can be called a field. So let's have a look at an example of a field, or multiple examples of a field. Okay, so the real numbers together with addition and multiplication. The complex numbers, now remember the set of complex numbers is the set of all A plus B times I, such that A and B are both real numbers, and I is equal to the square root of minus 1. So this, as a field, is isomorphic, meaning has the same algebraic structure as R2. So is isomorphic to 2 space over real numbers, meaning the correspondence, just abbreviate correspondence to correspond, the correspondence preserves the algebraic structure. Okay. And what I mean is, if you have a map from the set of complex numbers to R2, or a function from the set of complex numbers to R2, vectors in R2, then, and let's call it phi. So, for example, phi sending complex numbers to R2 by phi of A plus bi equals the vector AB. then this map phi or function phi preserves the algebraic structure, meaning that phi of a1 plus b1i plus phi of a2 plus b2i is phi of the sum of those two complex numbers. And the same or similar for multiplication. And we would say that phi is an isomorphism of fields. All right, so that's a bit of a digression. Now, another example of a field R3, right, which is a set of all vectors a, b, c such that a, b, and c are real numbers. Okay, so that's an example of both a vector space over this, but it's also a field. Or is it? Hang on. Anyway, okay, so not a field. Or, okay, another example of a field, set of rational numbers, fractions a over b, such that a and b are integers and b is non-zero. So you might be able to give this a field structure, R3, but it's not a field as is because you need a multiplicative structure on these vectors. So let's say you would need a multiplicative structure to make this a field on its own, right? Okay, so examples of not a field. So what is not a field? Set of integers, not a field. So dot dot dot, -3, -2, -1, 0, 1, 2, 3, and so on. And why is this not a field? Well, you just take an arbitrary element, say 2. So 2 has no multiplicative inverse. In the set of integers. So for example, 2 to the -1, that would have to refer to 1/2, but 1/2 is not in here.